Hey guys, Mr. C here. This is part 2 of the range equation videos I'm making. In this video, we're going to derive the general range equation where you're starting at some initial height, we're going to call it y initial, and firing a projectile. So, very similar to what we did in the last problem, we're going to try at the end of this video to have expressions for the total time of projectiles in the air, the maximum height it obtains, and eventually the range of the projectile. At the very end also we'll touch upon optimum launch angle for maximum range. So, in the same habit that we did in the previous video, we're going to fire a projectile up in the air. It's going to follow its parabolic path down towards the ground, and we're going to label a few pieces. First off, somewhere along the way, we're going to label that it's going to achieve a maximum height. It's going to take some time, we're going to call it time up to get to the maximum height. It's going to fall for some time down from maximum height to wherever we define as ground level. And the horizontal distance that it travels from start to finish we're going to define as the range. The very first piece you should know about this type of problem is because we're starting and ending at different heights, the time it takes the projectile to go up to maximum height is no longer going to be equal to the time it takes to go down to the ground because of the difference in distances. But a few things that will remain the same from our previous problem. The time it takes the projectile to go up to maximum height is still going to be the VI sine theta over g that we derived in the previous video. And if you forgot how we did that, I encourage you to look back. And in addition, we can actually quickly solve for the maximum height that a projectile will obtain. Because since the time it takes to go up is going to be the same as previously, our maximum height is also going to be the same. It's going to be VI squared sine squared theta all over 2g. But this time, because we're starting at some initial height, we're just going to have to tack on the y initial term, add it to it. And that's an expression for the maximum height. Now, recall, one second. Okay, here we go. So, recall from the previous that the range of any fired projectile is simply going to be the horizontal component of velocity times the total time that a projectile is in the air. So, just as we did previously, the range, I'm going to abbreviate as R, is going to be the horizontal component of velocity, which is just going to be VI cos theta. And now our total time, we're going to have to break it in two pieces, the time up plus the time down. Now, as we already said, we already have an expression for the time up, so all we really need is just some expression for the time it takes the projectile to fall from maximum height down to the ground. So recall at maximum height that the vertical speed of the projectile is 0 at max height. So what we can do is we can actually use the Freefall equation to figure out how long it is going to take to fall to the ground. So we're going to use the Freefall equation, d equals 1/2 gt squared. I'm going to specify that as the time down squared. And also note that the distance that it falls in the vertical direction is going to be equal to the max height. So that's simply going to be y initial plus VI squared sine squared theta all over 2g. So what I'm now going to do is I'm going to do some algebra and solve for the time down. So I'm going to multiply by 2 on both sides, divide by g, and take the square root. And when it's all said and done, I get a time down equals square root of 2y initial over g plus 2's cancel out. So vi squared sine squared theta all over g squared. Awesome. So now I have the time down, I have the time up. I can now go ahead and plug this into my range equation. So I'm going to put everything together, and for my total range of fired projectile, my general range, if I start on a height, I get range equals my horizontal component of velocity, which was VI cos theta, times my total time, so I'm going to write time total, which equals time up plus time down, just to remember. And so my time up was VI sine theta over g plus my time down, I'm going to go ahead and scroll up just to have it, plus the square root of 2y initial over g plus vi squared sine squared theta all over g squared. Now the very last thing we can do is we can do a little bit of math to simplify this, make it a little bit more pleasing to the eye. And so after you factor out some g's and do a little bit of simplification, you get to the end result for the range equation, which is going to be vi cos theta over g times, in brackets, vi sine theta plus square root vi squared sine squared theta plus 2gy initial. And there is the general range formula. Now, the first thing we should know about this formula is for any general formula we derive, it should always be able to reduce to the specific example. So what I mean by this is, in the previous video, we derived the specific range formula when you start in an unlevel ground. Our range equation, the one we just derived now, should reduce to that in the case where we start and end on level ground. So, in the case where we start and end on level ground, y initial is 0, so level ground. So what I'm going to do is I'm going to go ahead and I'm going to plug in my y initial to make sure that this range equation reduces to the previous range equation, which I'll have you recall was vi squared times 2 sine theta cos theta over g. And of course we did the double angle formula, but I want to leave it like this. So I'm going to go ahead and plug in my y initial of 0 into this equation. Notice that the only y initial is in this term right here. So when I plug it into 0, that whole term collapses to 0, making it nothing. Now I have the square root of v squared times sine squared, and so I take the square root of that, the squares just go away, so I get vi sine theta. And this whole term in the brackets is just vi sine theta plus vi sine theta. Well, adding those two together is simply going to turn into 2 vi sine theta. And now I'm simply multiplying the two terms together. When I go ahead and do that, the vi's become vi squared. I have a 2 there, and then I have a sine theta cos theta all over g. And note that this is in fact exactly the range formula that we derived in the previous video. The very last thing I'd like to do is I'd like to go all the way back to the range equation, the general range equation we derived, and I'd like to talk about optimum launch angle. So in the previous video, we looked at the specific range equation, and this, using the double angle formula, turned into vi squared sine 2 theta over g, and we used the fact that sine is a maximum when we have sine of 90 degrees, because sine of 90 is 1, so that helped us show that a theta of 45 produces the biggest sine and the best launch angle. If you look at this general range equation, though, it gets a little trickier. So if we look at this equation, notice we have an appearance of cosine theta here, we have a sine theta there, and then we have a square root of sine squared theta plus a couple of terms in there. And what I'd really like you to note is, when you have the general range equation, when you fire a projectile off the cliff, it's no longer as simple as saying the optimum launch angle is 45 degrees. It's completely dependent on your initial conditions, namely the speed you fire the projectile at, and more importantly, the height of the cliff. Those two things will have a determining factor in what the optimum launch angle is. So in other words, depending on the scenario, you could have any launch angle between 0 and 90 degrees be the optimum launch angle depending on your initial height starting off the ground and your initial velocity that you're launching a projectile with. I mean, not 90, but all right. So hope that helped you guys out. Again, we derived the general range equation, the total time the projectile was in the air, and we solved for the max range. All right, best of luck.